So I pulled up a blank page so that I could start with some math. I wanted to talk about converting um, concentration units. Um, and I just briefly mentioned what Tro talks about. So let's just try a sample problem that you know would be an example of this. Let's say we have a mole fraction, and I want to go to a molality of, let's say we have a mole fraction of X ethanol, that's short for ethanol, is 0.20. That means, of course, it's in water, so X H2O equals 0.80. What's the molality? So we know we have a ratio of moles, so we know essentially how many moles we have of each thing, and from moles we can go to grams, and from grams to kilograms. So if I have, let's say I have one mole total, then I have 0.20 mole ethanol, and that's going to equal, let's see, what's 0.2 moles? And I pick on ethanol because I know it's something that's miscible with water. Um, Ethanol has a formula of CH3CH2OH, which would be C2H6O. So that is 24 plus 6 plus 16. So 24 plus 16 would be 40, plus 6 equals 46 grams per mole. So I have 0.20 mole times 46 grams per mole. That would be a total of, well, actually I don't even need to figure out how many grams of this stuff I've got, but if I did, I would calculate. In fact, we could even do something like mass percent, in which we could, let's try mass percent as well. Um, so I have 0.2 moles times 46 grams per mole would equal, that would be 9.2 grams of ethanol. And if I have 0.8 moles water, 0.8 times 18 grams per mole, that's going to equal, and this is, I do need to know the amount of, that's going to equal let's see, um, I should be able to figure that out, but I can't at the moment, so let's just use Excel. And we've got 14.4 grams of water. So first of all, let's try the molality. I have 0.2 mole to 0 mole ethanol per 0.0144 kilograms of water. So now we can just calculate that out. And that would be 13.9 essentially molar, or molal, or essentially to 2 sig figs 14 molal. Okay, let's look at percent. So that's the mass of ethanol over the mass total, and we have both. So we take 9.2 plus 14.4. That's 23.6 grams. So then I take 9.2 over 23.6 times 100, not 1,000, 100%. Like I hit the wrong button. 9.2. There we go. And that gives me 38.98, which would be about 39%. So now we have equals 39%. Now if I had densities, I could figure volume percent and things, and I would probably need a density of the solution in order to figure molarity as well, because of course that's a volume function. But we can, without a lot of data other than just the molar mass, go from mole fraction to molality and to weight percent of ethanol in water. So this is a problem I was just doing, and I just want to show how these conversion factor, how the conversion works, because Tro just says a little bit about, convert each piece and etc. So I wanted to take something that seemed fairly complicated, like turning a mole fraction into a molality, and also we also did mole fraction into mass percent, and taking ethanol in water, So we have a 0.2 and 0.8 mole fraction ethanol water, and we convert the water to from moles. Consider we can have any amount of water, so I just say if we have 1 mole, then we would have 0.20 moles water and 0.80 moles of, or sorry, 0.20 moles ethanol and 0.80 moles water. Use molar mass to convert into grams. Really, for the molality, you only need to convert the water into grams. And then you take the water in grams, or the ethanol in the moles of ethanol over the water in kilograms by dividing by 1,000 from 14.4123 to so now you have the moles over kilograms water, which is the definition of molality, and that gives me 13.9 molal, or roughly to 2 sig figs 14 molal. And then percentage, we convert the ethanol to percent using the formula of ethanol, which is the that looks like methanol, but it's molality of ethanol. You take the ethanol is where did I have it here? CH3, it's CH2OH, which is C2H6O, and that gives you a molar mass of 46 grams per mole, multiplied by 0.2 gives 9.2 grams of ethanol. And then we just put one on top of the other, multiply, or first we add the two together to get the total grams, put the ethanol, divide it by the total grams times 100, and that gives you the percent. So it's really just following the units. Okay, let's get back to oh, cool. Thank you. So I have actually recording on Camtasia as well. How are you doing tonight? Did you have any questions on anything before I go on? Okay, cool. Yeah, just if you do, just write them in. For some reason, it's not dinging or anything, but I'll keep an eye out. Okay. So colligative properties, we looked a little bit at boiling point and melting point in class, and this is sort of what I was showing. If you have a pure substance, essentially, I don't think it doesn't show the pure substance, but these arrows would be going equally in toward vapor and toward condensation into the liquid phase. But as soon as you reduce the amount of the liquid phase, you're reducing the amount of molecules available to make vapor, so you reduce that arrow, but the other arrow stays the same. And eventually the two arrows match when you get less vapor, and that of course translates into a lower vapor pressure. If you do something like this and put in a closed container two solutions, one of which has a solute in it and the other of which has no solute as pure solvent, let's say you have maybe calcium chloride, that's what people like to use to pull humidity out, and water in the other, the water is going to come into the vapor phase at a certain rate. The water from here is going to come into the vapor phase at a lower rate. The condensation in each is going to be equal, but since less water is coming out of this one, since it's a solution and there isn't as much water available with the solute present, then you have a net flow of water, and essentially what's happening is this level will go down and this level will go up. And you can think of it as sort of the water trying to make the concentration of the solution in this beaker the same as the one in the other. In other words, zero concentration. So over time, you would see something like this. This would actually be an interesting thing to try with a desiccator. And in reality, people do something like this. If you have ever used a product called Damprid, you have basically this mesh container with little pellets in it, and this is held over a bucket. And what happens over time, you put this in a closet or a recreational vehicle or whatever you want to keep from getting moldy, and this stuff in here disappears and this bucket fills with liquid, sort of a thick liquid, because it's saturated in salt. This salt is actually CaCl2, and it traps the water because the rate of evaporation from a really strong CaCl2 solution is very small, and the rate of condensation is still fairly large. So if you have little droplets of water out here that are pure, they will end up in that bucket. They will evaporate and end up in there. So you actually, if you go to Home Depot or Lowe's and buy Damprid and put it in a closet, you're using this type of principle. So this is really sort of an expression or extreme. Here we're looking, with this case, we're looking at a solute that's not at all volatile. But you can also sort of extend this to solutes that are volatile, and that is what Raoult's law is about. Raoult's law basically says that if you have the vapor pressure of a mixture, you take the vapor pressure of that material in the pure form and you multiply it by the mole fraction in the mixture. So the change in vapor pressure would be the vapor pressure of the solvent minus the vapor pressure of solution, which is going to be this is P solvent minus P solvent times X solvent, because of course that's X solvent, right? That's the definition of the P solution. So I'm saying that P, if I look at the change in vapor pressure, it's the P pure solvent minus P solvent times X times the mole fraction of the solvent. Well, notice that we have P solvent and P solvent, so we can take that and put it to this side and say it's P times 1 minus X. Well, the definition of mole fraction, 1 minus X solvent, this is now equal to X. If it's a two-part solution, it would be equal to the mole fraction of the solute. Remember, they have to equal 1, so 1 minus the mole fraction of the solvent is equal to the mole fraction of the solute. So now we have, that's where you get the delta T equals X solute times P0, not delta T, sorry, delta P, VAP, P solvent. So that's the result then with vapor pressure lowering. Now, with the volatile solute, with Raoult's law, you have on this side, as an example, you have a pure solute, and let's say maybe it's toluene or something, which is not very volatile, so you just have a few of these molecules in the air. On the other hand, you have another solid that's actually has a very high vapor pressure. Maybe this is something like pentane. Pretty volatile stuff. Now when you mix it together, you have half as much pentane. Let's say this is a X equals 0.5 mixture of toluene and pentane. Now the toluene, you only have half as much in a vapor phase because really you have half the concentration in the solvent in the solution phase. But the pentane, you also have half as much in the vapor phase. 1, 2, 3, 4, 5. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And here you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's cut exactly in half as well. And if you think of the total vapor pressure, clearly the vapor pressure of the mixture is less than pure pentane because toluene is less soluble. The vapor pressure of the mixture is also greater than that of pure toluene because, of course, you're mixing it with a more volatile solvent or a more volatile material. So what you would end up getting is like an average. This would be sort of the average of the vapor pressure of these two. And what you're sort of describing would be this type of a graph where you might have the toluene over here and the pentane here, and you're looking right in the middle here, so you're seeing just that average of the vapor pressure. That's not always the case. This is what they call an ideal solution. And an ideal solution really means that the interactions between the solvent and solute are equal to what they are together. So if you think of intermolecular interactions, you have solute and what you're saying in an ideal solution is that these interactions are equal. So that basically they behave as though they're just mixing together but not changing their interactions. Now you can get lots of solutions that exist that don't have ideal interactions. So for example, if your interactions were stronger, so your solute solvent is greater than solute solute and greater than solvent solvent, you might get something like this where as you mix them, the vapor pressure is actually lowered of the mixture compared to the other two. Now, on the other hand, you could have the other where the solute actually and the solvent actually break up their interactions. In that case, the solute solvent interaction is less than solute solute and less than solvent solvent, and then you get this sort of the opposite, sort of an upward curve. where the vapor pressure is actually greater than the of the mixture is greater than the compound than the average of the two vapor pressures, the weighted average of the two. This is a good website. I probably not sure if yeah, I don't think it's active here, but you can I think I have this also on the slides that are online. You can look at this website and get a lot of good information about this and about its relationship to distillation. I'll go into it a little bit. This is one of the big uses of Raoult's law, and that's distillation. Um, you take and heat something up to convert it into a vapor phase. The more volatile thing will be present in the vapor phase in a greater amount. Just like if you think of if you had a mixture of these two things, this one over here, which I'm just calling pentane, would be there. If you had a 50-50 mixture, the mixture up here is much more than 50-50. Here in in the liquid phase it's 0.5, but in the vapor phase it's not, because now you have it's 3 to 9, so this is actually the X of the vapor phase would be 0.3 toluene and 0.67, so 0.33, 0.67 uh, pentane, if we're calling these arbitrarily those things. So it's, instead of being 50-50, it's not anymore. It's much more concentrated in pentane than it is in toluene. Um, and that, if you took that vapor and then condensed it, you would get a liquid that is now not a 50-50 mixture. It's concentrated in the lower boiling material. So that's a single step. Now imagine if you could take that stuff, so you could take this stuff and boil it out. So you start out with 50-50, you boil it up and you end up with a 67-33 in the vapor phase. You turn that back into a liquid again that now is 67-33, and then you vaporize it again. Now the vapor is going to be much more concentrated in this vapor phase still. It's going to be more like, well, take it a third and a third, it's more like now closer to 90-10, and then you condense it again and so forth. So if you condensed it enough times, you would end up with a 100% or 100-0 mixture, 100% of the lower boiling. And that's exactly what a fractionation column does. It distills it many times, and eventually you end up with very high concentration of your lower boiling mixture at the top of the still. Each time it distills is called a theoretical plate. So let me just label this as a fractionation column. And the each distillation is a theoretical plate. And in reality, in refineries, they actually do have theoretical plates. They have a fractionating column. If you go to an oil refinery, the first thing you'll see are these big, huge towers. And those are fractionating columns, and they're really divided into these layers of plates. So on one plate, you'll have a certain temperature. The vapor goes up and then hits a bubbler. It goes down into this, and whatever is that boils at that temperature condenses, and then you have this liquid and you're drawing it off into a tank. But what is higher boiling will go up to the next plate and so forth. It goes into this through a tube and then a sort of a bubbler that will bubble up through the next solution. And eventually at the top of the still you have very high boiling things like so way up here you would have things like petroleum ether with a boiling point of about 30 degrees Celsius maybe. And down here you might have, at the bottom end of the still, you might have fuel with a boiling point of like 200 degrees Celsius or so. So you can see how that's where that term theoretical plate really comes from. The stills in an oil refinery have actual plates that hold layers of liquid. Okay. So if you look at the vapor pressure, if you remember, the vapor pressure and the boiling point are quite different. The boiling point is simply the temperature. So now instead of mole, we have mole fraction still on the bottom, but here we have temperature boiling going up. And so something with a high vapor pressure is going to have a low boiling point. Something with a low vapor pressure is going to have a high boiling point. And since the boiling point and vapor pressure are not equal, are not linear with each other, I mean the boiling point, and if you think of vapor pressure and temperature, vapor pressure is proportional, or Ln vapor pressure is proportional to 1 over temperature. So vapor pressure equals E, or is not equal to, is proportional to E to the 1 over temperature. Actually, it's negative 1 over temperature is proportional to negative 1 over temperature. So vapor pressure is equal to negative 1 over E to the negative 1 over temperature. So it's clearly not a linear relationship. So when you get this, you draw a curved line. And if you start here at, say, a 50-50 mixture, what we did at the start, we came over here, it's 50-50. And if you look at, that image that I was showing, where you ended up with now a 30-60 mixture. So when it's 50-50, it would come over here to about a 30-60, and it would condense. That would be your distillation. Now here it would boil and come over to maybe a 90% mixture and condense and so forth, and you could draw a line to these points and they would sort of define a curve something like this. That would be the curve. And this is sort of what's used to think about distillation. You start out with a concentration here, you boil it, you condense it, you end up with a concentration here, you boil it again, you get this concentration, you condense it, you get that concentration, you boil it again, and now it's pretty much 100% of your lower boiling mixture. So what happens when things get tweaked and you don't have an ideal mixture? Then you get things like maxima. So this is a case of ethanol and water at a mole fraction of 0.1 water and 0.9 ethanol. You actually have a maximum in the vapor pressure, which is in turn a minimum in the boiling point. And this is percent by mass. It ends up being about 95.6. So they've gone from mole fraction to percent by mass, and that's why you have the point here in mole fraction. It's over here in percent by mass. So where this is a maximum, this is now a minimum. And on the other hand, you can get another type of, I guess I didn't bring it up here, but if you mix something like ammonia in water or something like that, you might get a boiling point that would be decrease actually, and then or actually you get a vapor pressure that decreases, which would be a boiling point that it's some mixture increases and then decreases. I look for those slides and pull them up, but so you can get the opposite where you have a mixture that has a, actually, sorry, backwards, you can, yeah, vapor pressure decreases, yeah. So you have a boiling point that now becomes a maximum at some mole fraction. If you have essentially this type of a deviation. Okay. So we looked at boiling point elevation. Next thing I'll do is look at freezing point depression. I'll probably do that. I think I'm going to probably record something on Monday about the same time, and then Tuesday and Thursday I'll also be doing a recording. So we'll look at freezing point depression, and then what is it? Trying to think. And osmotic pressure would be the other thing, the other colligative property to look at. Another piece in this chapter I'll still need to do is the part on enthalpy of mixing, which is sort of an interesting process. Any questions on what I've done so far in this? Let's see. Oh, little, yeah. It takes a while of getting used to it. I would suggest going to that. Or are you talking about graphing with what we've been looking at in this talk, or graphing in general? Oh, what I just went over. Yeah. It takes a while looking at it, and you got to remember when you're relating these graphs, which are typical distillation graphs. Oh, yeah. As what I'm saying here, as vapor pressure goes down, if you have something with a low vapor pressure, the boiling point increases. So if you look at this vapor pressure graph up here, this piece here has a vapor pressure that's lower, and it would map, actually that part of the solution maps into a boiling point that is higher. Oops. That is higher than that. So this compound that has a lower vapor pressure maps into a higher boiling point. One that has a higher vapor pressure maps into a lower boiling point. And I guess what I'm saying about vapor pressure and boiling point as well is if you take the boiling point is the temperature when vapor pressure equals atmospheric pressure, whatever that atmospheric pressure is. You know, if you're sea level atmospheric, that's 760 millimeters, but if you're, you know, it's someplace else, it could be quite different. Now, if you look at vapor pressure and temperature, you have the Clausius-Clapeyron, which says that ln pvap equals negative delta H over R times 1 over T plus C. So what it's really saying, if you're thinking of a proportionality, whether something's linear or not, is that if you take the pvap, the ln pvap is linear to 1 over T. But if you think of vapor pressure is going to equal, you take E to this side and E to this side, it actually equals E to the negative delta H over R times 1 over T. So the proportionality is different. The proportionality here would, or if you think of what it's proportional to, so you could say pvap is proportional to E to the negative 1 over R, because these are just constants here. Over R, sorry, over, not R, negative 1 over T, because R and negative delta H are constants. So you take that negative over here, and you get pvap is proportional to E to the negative 1 over temperature as you're changing temperature. So, and where that now is going to equal a constant, you set it equal to 1 atmosphere, and that would give you your boiling point. That is why you don't get straight lines in that graph of boiling point, because you're actually taking an e to the negative t function rather than a simple linear function. I know, does that help? I know it is complicated, but I would suggest also going to this website, because they probably actually explain it better than I do. This website here. Not sure if I can. Tried control, it doesn't seem to work on this, but you could give it a try. They explain it pretty well, mixing different things that are both ideal solutions and non-ideal solutions. Okay, thanks. And okay, thank you. So have a good evening. If and I'll be back on Monday, Monday night, doing the same thing. Okay. So, and have also a good weekend. Thank you.